Yeah, you've heard a lot of me already, so I will make this a short talk so the administrators of the building don't get mad at us for not leaving on time. Actually, I don't have all that much that I need to say. I'll probably talk for 7 or 8 minutes and then try to open up some discussion on the topic. So I mean, we're all quite familiar with the recent breakthroughs in deep learning perception processing, and as well with the sometimes excessive hype attached to these very real and interesting achievements. So I wanted to talk a little bit about how these deep learning architectures relate to AGI, to some issues with them, to some attempts to work around these issues that I've been experimenting with some students recently. So as I've gone over earlier, while my main approach to AGI is not a classic subsymbolic deep learning system, I've been experimenting for 6 years now or something with some of HMR's stuff, which is a classic deep learning architecture applied to vision and audition. And one thing I've thought about a lot in talking to Itamar and a bunch of others, and I apologize for showing a slide that is too small for anyone to see, but at least I can read it. So I want to put a pitch out there for a book by a guy named Stellan Olsen, who I've never met, but it's a quite good book. So this book is called Deep Learning: How the Mind Overrides Experience, but it has not tremendously much to do with stacked autoencoders or convolutional nets, or any of the currently popular deep learning algorithms. Rather, it's more of a cognitive science treatment of the theme of deep learning, and he comes out of more a symbolic production system, like classic AI background. But his point in the book is that deep learning is really about the dynamics of processing and the interrelations between different representations in a network, rather than about whether you're using a neural net or which particular algorithm you're using. So, I mean, key points that he associates with deep learning, I mean, the spontaneous activities, so a cognitive system always doing things, structured representations that are built out of other representations, given a hierarchy of representations down to the lowest level. You have a lot of feed-forward processing going up in layers from the bottom to the top. The processing units have limited capacity, often pass along less information than they took in. Not all of the representations learned are stored in long-term memory. So some are thrown out. You have generally local coherence within each local node or processing unit, but you don't enforce a global consistency. You do have feedback from the top down to the bottom. A small change in any one place could potentially cause a large change somewhere else via these feedback dynamics, which is a complex, possibly chaotic dynamical system. And you may have conflicts between different parts of the system that aren't noticed until certain processing happens. And then, broadly speaking, you have some kind of reinforcement. The whole system has to do something. How well it does it goes in and refines the representations internally. So this kind of hierarchical processing dynamic with local coherence, perhaps global inconsistency, feed-forward and feedback processing. I mean, this is deep learning of representations. This can happen in a formal logic-based theorem-proving system. It could happen in a neural net. It could happen in some kind of genetic programming system. It could happen in an open-cog atom space. I mean, that process is important and is a key part of human intelligence, probably needs to be a key part of any general intelligence operating under limited resources, although that hasn't been rigorously proven. But one thing I see happening a lot in more popular media type discussions of deep learning, and occasionally in more academic discussions as well, is that these general principles, which Olsen articulates nicely, are somehow fudged into the specific deep learning neural net architectures that are commonly used, recurrent neural nets, autoencoders, or whatnot. I mean, in a perception processing context, those particular neural net architectures are the best functioning manifestation of these principles that we have, but that doesn't imply that these particular technical architectures are going to be the best manifestation of these principles for, say, language learning or mathematical understanding, or for learning to do complex actions and manipulations for that matter. So I do think it's important to understand the context and the way in which deep learning, broadly speaking, is important to AGI, and also to understand the limitations of the specific kinds of deep learning algorithms that are currently proving so successful in particular perceptual domains. So in that vein, again, to cite some other people's work, I'm going to cite a couple examples of strange behaviors by currently very successful deep learning algorithms. And if you haven't seen these papers, these are pretty cool. I mean, this was a paper from 2014 by a group of researchers. So here we had convolutional neural nets with extremely high accuracy trained on ImageNet. Now, those nets believe, for example, that this is a starfish. That's a jackfruit, right? So these networks have very high accuracy on ImageNet, which consists of real images of things. But if you feed it these made-up images, they classify them with extremely high confidence as being these familiar objects. Now, that's a very interesting kind of overfitting, because it's not overfitting in the most direct and obvious sense, because, I mean, they did proper in-sample, out-of-sample training on their image corpora, but it's overfitting to the variety of images that exists in the whole ImageNet, right? Now, a human being, because we're doing a different kind of learning, we're not going to mistake those as starfish, jackfruit, centipedes, and so forth, even though we have not been trained on that kind of image either. So that's sort of, it's an indication that whatever these currently successful deep learning algorithms are doing, although it may resemble the visual cortex in some way, also has some significant differences. Now here's another example, again, convolutional neural nets. All the images in the right column are classified incorrectly as ostriches. The images in the left columns are correctly classified. The middle column shows the difference. So this is an ostrich, that's an ostrich, that's an ostrich. These are all classified correctly. The differences are a handful of pixels between the different images, but that very small percentage difference between the images is enough to make it an ostrich rather than to make it the image that you think it is. Now, I mean, granted, people found these pathological images by searching for them explicitly, right? So if you just show it a random mutation of that cute little dog, it probably won't think it's an ostrich, but still, a person's not going to think that guy there is an ostrich and that is a dog, because it's really, really similar. So these pathologies don't necessarily matter that much in practice, because these kinds of images are low probability, so they're not going to affect the error rate very much. But they're an indicator of some fundamental difference between what's happening in these networks and what's happening in biological systems, even though there's also some similarity of architecture. And I do think the way the human brain does visual perception is deep learning in the broad sense that Olson has outlined. But yet I don't think it's the same thing as what convolutional neural nets or stack denoising autoencoders are doing. And one piece of evidence for that is these peculiar pathologies from the most commonly used deep learning systems that we have today. Now, what do I think is the critical difference? So here's an example from a different sort of deep learning system, which gives much worse accuracy on the training corpora so far, and hasn't been banged on remotely as much, but has something in common with human perception that I think these more common algorithms don't. So this is from a paper on the stochastic image grammars, right? And what these stochastic image grammars try to do is take an image and decompose it into pieces. And I mean, that's very nice, and it's sort of what popular media leads to believe the most common deep learning algorithms do, but isn't quite what they do. So ideally, if a stochastic image grammar worked, you would look at that picture, you'd say, okay, well there's a face, there's some ears, there's a body, and you'd build a graph, like there's the face nose, there's the ears nose, there's the ear node, there's the earlobe node, and you decompose it into pieces, right? And I mean, that's a nice idea. No one ever got that to work tremendously well. They got to work on a bunch of toy examples, and they never got to work with extremely high accuracy on a corpus. On the other hand, while that's I mean, these handmade examples are too pat and too pretty to come out of a real system. I think they have something to teach us. And one of the things I'm working on now is to try to get deep learning algorithms, particularly stacked convolutional autoencoders, to tweak those algorithms in such a way that they will give a nice hierarchical breakdown of the features in an image. So basically, take the algorithms that currently work really well and modify them a bit so that they're building meaningful internal representations. Now that are internal representations that seem meaningful to me as a human being, right? I mean, that doesn't necessarily improve the classification accuracy on ImageNet or CFAR or MNIST or these standard corpora. On the other hand, if what you want to do is recognize patterns in the deep learning hierarchy and feed them into a system like OpenCog, it helps a lot because you're getting the internal structure in the deep learning hierarchy that you want. So I mean, if you take this is simplified because actually we have overlapping squares, and this doesn't show overlapping squares because they make the picture uglier. But you have a hierarchical network where you have nodes referring to small image regions at the lowest level, nodes referring to larger image regions as you go up. And then if you basically train a denoising convolutional autoencoder guy here to predict what happens in this little square, and the inputs to that network can be the things below, they can also be siblings or things above, then with that sort of way of sort of breaking down your deep learning network with predictors for local regions, then you get predictions of what occurs in each part of the network, and you can get a high accuracy overall, but you can also ask like, what was there, and it will tell you what was there. And this, so we've just been, by we I mean other people doing the actual work in this case, but these are some Google Summer of Code students, generously funded by Google, and then one of our staff in ICOG in Ethiopia. But in experimenting with this over the last few weeks, you can get on the CFAR corpus of small images, which is what we've been playing with, accuracy about the same as with standard deep learning algorithms, and in the 70% or so range. And not world-beating accuracy, but decent accuracy on the corpus, just for the first pass without tuning things. But you also get meaningful local representations internally. So this is the paper that was submitted to the proceedings kind of discussed the general idea, but that was submitted a couple months ago. And now there's actually been work going on this in the summer, which is still preliminary and not published anywhere, but seems to be working. And that's the goal here being to make something that's accurate, but also tells you locally what exists at each part in an image. And then you show that network many images, and you look at what are the common patterns in the state of the network over exposure to many different images, and then put those patterns into OpenCog. And then there's various directions you can take it from there. For example, we've been playing with putting one of Jürgen Schmidhuber's long short-term memory networks in each node instead of an autoencoder-decoder pair, because the LSTM keeps a memory of sequence, and then that can be potentially better for video processing, but we only have weak evidence for that now. So the general message I wanted to convey is, I mean, deep learning as a broad principle, which Olson articulated so nicely in his book back in 2006. Deep learning as a general principle is quite important. The currently most fashionable deep learning networks have a lot of weird aspects, as these examples showed, and those weird aspects reflect some fundamental differences in what they're doing from what humans are doing and from what I would consider cognitively meaningful. So an important research direction, which is not unique to me, but is being pursued by others as well, an important research direction is how to take what's good about current deep learning architectures, which is basically their ability to perform with high accuracy on classification tasks so far, and try to morph those algorithms in various ways so that they build meaningful internal representations. And that's useful for a lot of reasons. I mean, it's useful for question answering, it's useful just for image understanding in various applications. It's also useful if you want to take a deep learning network and hybridize it with other types of AI components and use it as part of an integrated AI system. Because ultimately what you need there is not just to know whether you're looking at a cat or a chicken, right? I mean, you want to know where the cat's nostrils are and the cat's eyes are, and you want to be able to compare the cat's eye to a dog's eye. And you don't want to have to do that by segmenting each part of the image and then training a separate supervised learning classifier on each part of the image. You want the understanding of the image parts and their relations to emerge organically from observing the image in the first place. So that's basically it. I go over that in more detail in the paper. So I sort of was hoping for some commentary and discussion, because I think probably all of us have been impressed by these deep learning results and probably a bit skeptical in our own ways about how much they teach us about AGI, but also curious and interested. So probably there's a lot of thoughts and comments here. Okay, let's say, Josh has just showed up. You can pass the microphone.
Thank you. With respect to these aversive training examples that aversive examples that have been generated by mutating the input until you maximize the result of certain output neurons, I found it very interesting, and of course there have been many publications recently on that, and some people suggest that it's mainly a lack of regularization that ought to take place. For instance, if we apply something like a Gaussian filter to the input, that is, we require neighboring pixels to be somewhat correlated, then most of the aversive examples are no longer possible. Which means, just imagine we take some electrodes and poke them into the visual cortex to generate some inputs that are theoretically possible, but way out of the normal specifications of the network. And then you get some aversive results that wouldn't be so frightening to us, because it's stuff that cannot appear in the nature of the information processing of the brain. Certain inputs are not possible because of the way the pipeline is built. Another effect that it was not in this publication that I just referred to, I forgot the name, is that we are trained with a lot of noise. That is, we get a lot of examples in our input that is extremely noisy and that is not a clear image. So humans are not trained on ImageNet, but they're trained on extremely shitty data. And this means that we are very good at recognizing a clear image from shitty data and have networks that are specifically able to handle that. So there might be ways around handling that don't make us leave the deep learning paradigms as such. There are other approaches, of course, the mathematical structure, classifier surfaces, and differences of prototypes to classifier surfaces, but let's not go there for a moment. There's this deeper question: how much does deep learning teach us about the brain and the mind in general? And how far can we go with it? And it might be the more interesting question. Is it part of a larger architecture, or is it a single principle that can explain most of the mind? I tend to be in the former camp, but it would be very interesting to see arguments for the latter.
No, I'd say you're probably, the literature on these apparent pathologies is currently ongoing, right? So people can find ways to make them go away, then someone may find another way to make the pathology appear after that mechanism is inserted, and that's going to take probably a few more years of papers back and forth to unfold, right? So I'm not absolutely sure about that. My guess is, if it's not building a cognitively natural representation internally, you're going to find some weird way to trick it if you're clever enough. But that's just got to be shown through the unfolding of the literature, right? I mean, one thing you said is you think we can solve these problems without leaving the deep learning paradigm, and I pretty much agree with that. I mean, the tweaks that the students working with me are applying to try to get a more natural representation, I mean, these pretty much are within the deep learning paradigm anyway, but we're rearranging stack denoising autoencoders in a different way, but it's maybe a good idea or maybe not. It seems good at this moment, but it's within that same paradigm, but we're trying to do this for vision and auditory processing. We're not trying to blow it up into a whole AGI architecture. And in my view, that specific kind of system is useful as a component of an AGI architecture. I mean, Idemar, who didn't come this year, but he disagrees. He basically thinks more like Demis Hassabis did when I last talked to him, and David George, that this sort of architecture can be used as the start of an AGI system. First you solve vision and audition, then you add some reinforcement to it. Then you kind of build out this neural net deep learning system until you get a full-fledged AGI mind. Yeah, I tend not to think that's the most fruitful approach either, though I can't prove it won't work.
I think we need to differentiate between conv-nets and deep learning. Conv-nets are probably not going to carry us all the way, and these principles that you showed with the Olson book are much broader than conv-nets or autoencoders. So let's also bear this in mind, it's not the same thing. Conv-nets are a particular kind of network architecture that does some things with the information that it probably shouldn't be doing.
Yeah, but I think that even the broad principles that also articulated about deep learning, I mean, I don't think those are the only principles of the mind either, right? I mean, this hierarchical information processing is one important structure of information processing in the mind. I mean, it doesn't say much about goals and motivations as you have in your own work. I mean, it doesn't say a lot about actions, and it also may not say a lot about what we do when we're doing more complex deliberative reasoning. So I mean, I think those are, in my view, those are among important general principles of cognitive information processing, but are certainly not the full list, nor would those 10 necessarily be at the top of the list of 50, but they're up there somewhere, right?
Okay, suppose I had a detailed connectivity graph of your visual cortex. How do you know that I couldn't start with an image that anyone here would classify as a dog and do gradient descent and result in an image that, despite having very little Euclidean distance from what I started with, you would misclassify as an ostrich?
I don't know that. I mean, that's my hypothesis, but I haven't done that test.
Well, we have plenty of examples of human beings routinely misclassifying things that are called optical illusions.
But in different ways. I mean, it's a quite different pattern than what you see.
They are different, but the convolutional neural networks, if they could make a judgment about it, might judge our misclassifications to be as inexplicable as we judge theirs to be. Does it mean that we're classifying in a fundamentally different way, or simply that there are?
I think it does, but that would be a long conversation. I mean, I had a PhD student in the late 90s. I mean, he did these nonlinear dynamical models of what's happening in a lattice of different processing operators to give rise to human-like visual illusions. We also know about olfactory illusions, and it seems like the human-like visual illusions can be explained as properties of sort of very low-level generalization operations and so forth. I mean, you can, if you look at them, you can look at many of them as actually errors of a more cognitive processing methodology that you can understand. So I would bet when you, and had some evidence that when you actually dig into them, it doesn't look that way. Like the human perceptual illusions actually transparently come out of some comprehensible cognitive processes, which are quite different than these pathologies of convolution. It's like with the Muller-Lyer illusion, where you see the arrow with lines pointing in is shorter than the arrow with lines pointing out. I mean, you can look at that. That comes out of a certain kind of reaction to diffusion equations if you model them doing perception. But you can transparently see why that happens. The one looks longer because it stretches out in either direction.
But I mean, if you went back a few slides to the image misclassified as a baseball, to me that actually kind of looks like a baseball.
Maybe you have a convolutional neural network.
I may very well.
And nobody else does.
I don't.
Yeah.
It has the red stripes. I mean, you can see that it's doing something.
And does that look like a king penguin on the left side?
Not really, no.
Yeah. I mean, of course, these networks are doing something meaningful, right? I mean, they're very accurate at what they're doing. Yet it's not a baseball, and that one at the top is not a jackfruit. I mean.
Right. It seems obvious to us because we're relying on what our visual cortex is telling us.
Well, yeah, sure. I guess I would argue if we really did that analysis, and this may be textbook material in 10 or 20 years from now, the errors the human visual cortex makes, they dispute the things it's doing, but the things it's doing that lead to those errors are things that are useful for cognition in general, whereas the things the convent is doing that leads to its errors are not things that are useful for cognition in general. I mean, that is my hypothesis. I don't claim that that's proven.
Did you have a question first? Or? Okay. Well, Ben next.
Okay, I'm just wondering, so I'm basically a layperson here, but I'm looking at robots and trying to make them location aware. And I was thinking about how I would teach a robot to do that. And I think about myself, or when I look at kids, I think they must have some kind of four-dimensional representation of objects that they see. Like they have a kind of three-dimensional representation. Like I look at somebody, I know that the other person is behind them physically. And I also have the temporal relationship. When I move my eyes, then the fovea moves. So I need to remember where somebody was to actually have the relationship to that other person. But when I hear Ben explaining about those pictures, basically comparing static images, I don't think we ever do that. I don't think biological organisms ever compare static images. We always have a four-dimensional representation, and we create, maybe, I suppose, we create a kind of two-dimensional projection of that, and then we compare this two-dimensional projection to whatever image we see. Is that right, or is that being implemented in AGI?
That is right, and I think setting AGI aside, that's sort of the recognized next frontier for deep learning vision processing. I mean, the reason people work with images is because it takes less computing power, right? But I mean, you working on video, there are also papers published on video processing using very similar architectures. It's just that for the exploration of these particular phenomena, it's cheaper to do the experiments on images, just on videos. It takes less computing time, so people have done it that way. But the same principles appear to work, broadly speaking, for processing video. It just takes a lot of hard drive and processing time to do it. But that's the direction the community's going in. I mean, Google, Baidu, whoever has enough images, enough videos, and enough processing power is exploring exactly this sort of algorithm applied to videos now.
Yeah, so I think those mistakes that we have here become irrelevant in the moment you have temporal.
I think very close analogies of these pathologies would occur in a similar deep learning architecture applied to a video stream.
Mm-hmm.
It's just you'd have to show videos instead of showing pictures. But I bet the same mathematical phenomenon would occur.
Yeah, but when I'm thinking about the representation, I'm not thinking about videos in pixels. I'm thinking about sequences of objects, right? About sequences of three-dimensional representations of objects.
Well, the question is where those representations come from. I mean, it's the particular internal representations of a convolutional network that lead to these peculiarities, right? So if you have a convolutional neural net processing video data, its internal representation will probably lead to analogous peculiarities.
Let's put it another way. I think the computational complexity comes from the fact that we lose a lot of information in the video. The biological systems have the reference, like they know what angle they moved their eyes, right? So they know the relationship between the objects. They stay the same. So they can correct for that. They don't need to compare pixels to find the relationship between a sequence of images. Because if I know you're there and I look this way, I still know that you've been there, right? I don't need to compare my
something in your visual
peripheral
vision.
vision.
That comparison.
Exactly, but our machines currently don't do that, right? So they compare the images one by one or sequences of images. I'm thinking about a colleague in Switzerland who has a startup that makes imaging sensors that in the hardware they recognize movement. So they only recognize the changes in the picture, in a way compressing the data, but that's what our retina does as well. Right? In our peripheral vision, we don't see much other than movement. We are much more sensitive to movement than to content.
Yeah, but in the fovea, you register what's there, not just the changes.
Yes, but in order to have an image, I need to have a representation of what was in the fovea when it was pointing this way and what was in the fovea when it was this way. So I'm just thinking this is a huge reduction in the amount of data compared to video.
I don't know. I mean, the brain has an awful lot of neurons. If you like 100 billion neurons, about 30% of the brain is processing vision. So I mean, there's a lot of processors devoted to processing that video feed coming in from our fovea, right? I mean, say 30 billion neurons in the first approximation. So
I guess it's to be found out. I'm just surprised that it's not mentioned as a technique.
I think we're running a little late, but we're not getting kicked out yet, so we can do some more questions. Okay.
Hi there, Ben. So something that I was just was occurring to me as you were talking, and it's not to argue against what you're saying at all, but there's like a lot of examples where you see a particular image, and it might, say for instance, look like a skull, and in every way it looks like a skull, and then you look at it from a different perspective, and you see a hammock between a tree and what looks like, you know, a girl on the hammock and all this type of stuff. But when you look at it from either way, you're seeing what you're convinced is either from one perspective a skull, or looking at it from another perspective is this hammock. And so it seems like for us as human beings, we're animals. We're bringing in other cognitive processes which are influencing what we believe that we're seeing.
That's what you
and
model as the top-down influence in a deep learning model, right?
Right. So I mean, I guess just by looking at these examples, which seem so perversely, on the surface, seem so perversely wrong, you know, we can be so kind of perversely see such profoundly different things, like profoundly different objects.
I guess my reaction to that is the same as my reaction to this guy. It seems like a different kind of perversity. I mean, just like you can often understand how something works by seeing what kinds of mistakes it makes, right? So the fact that we make some mistakes and a convolute makes different mistakes, and I mean that correlates with the kinds of internal representations that these different architectures are building, right? I mean, we're far from perfect, but we make a certain pattern of errors. And
no
these
doubt.
systems make a very different pattern of errors.
Yeah, I guess my point is it's just kind of a reminder how we can see something that seems so semantically different out of the exact same image, right? And so
yeah, that's all from just felt psychology in the 30s, right?
Mm-hmm.
So my comment on this, and I don't know exactly how much work has been done to follow up on this sort of thing, but I've seen like adversarial training of neural networks, where you specifically are generating images that are designed to be misclassified and then training on them. And so it seems like adversarial training of this kind would be to a much higher degree immune to this sort of created image, because it's specifically been trained to be immune to them. And I believe one of these papers mentioned that, in fact, if I remember right, but I could be wrong on that. But I mean, as you mentioned, this is going to require more back and forth, seeing what kinds of techniques solve this. But it just seems to me that adversarial training is going to solve this.
In your feature learning work, are you attempting to auto-annotate the actual semantics of these features?
Yes.
Or these sub-features?
I mean, that's the idea. Yeah.
Okay. Like, how are you doing that? Like, based on the external world model of the types of things you're looking at?
So the basis has got to be unsupervised pattern recognition. So I mean, you're showing a lot of different scenes to the network, and you're saving the network state each time, and then you're recognizing what are the common patterns in the network state. So say, if you show many faces, there should be a common pattern in the network corresponding to eye and lip and so forth. And then, so the common pattern that common pattern is what we put into the open cog space. But then if you have many common patterns there, then you can recognize the individual spatial relations between them, which open cog already knows how to do. So you can recognize patterns like, okay, often when there's an I, there's another I next to it. Often when there's an I with another I next to it, there's often a nose below it. So once you recognize the recurrent pattern on a bunch of network states, then you can put that into OpenCog's space map after aligning things, and then we already have technology for identifying spatial relations among things. So then what you would learn from that is there's something which would be a nameless node in OpenCog, what we would call the face, and that usually has two eyes within it, but again, those would be nameless nodes, which are usually have a next to relation to each other. There's usually a mouth, which again would be a nameless node, which has a below relation to the eyes. And so if everything worked nicely, that's what you would get, which is just unsupervised understanding of habitually recognized subpatterns of the tree and their spatial relations to each other. Now, once you get cross-modal connections, right, then you may notice like noise comes from this space thing. Oh, the noise is associated usually with this repeated pattern rather than that repeated pattern. And then if someone says shut your mouth when you're opening it, then you may associate the word mouth, which came either from text or from auditory modality, with that particular pattern that was got through unsupervised mining of these trees. So that's what we're aiming for. And we did a little bit of that in 2010 or 11 using Edemar's destiny system to prove the principle. I had a paper on that in some previous AGI conference. But then what we found is when you get beyond really simple examples, the quality of the patterns we could extract from the library of destined states was too bad. I mean, it just wasn't good enough at recognizing the local features within the image. So then the research on that in the last couple of years has just been fiddling with the network to try to get a better identification of the features at each point in the image. And then in practice, what we do is we save the states of those networks and we run a frequent subtree mining algorithm on them, which is some open source code from someone else. So the frequent subtrees become nodes and links in open cog space. So I think that unsupervised pattern mining should be the foundation. And on top of that, you can have reinforcement learning and supervised learning to associate the unsupervised patterns with other things. But doing this supervised approach to recognize the features within the images, or reinforced learning approach to that, probably can't work. There's not enough reinforcement. Or like when a rabbit recognizes a tree versus a bush, probably it's not because a tree hurts its head when it runs into it and the bush doesn't, which would be a kind of reinforcement learning. Probably it's just some kind of unsupervised learning that the visual features of that tree are quite different than the visual features of that bush. And then other cross-modal experiences provide supervised additional knowledge and add on to that.
I would like to ask your opinion on the flows that you showed about deep learning algorithms. It seems to be a classical symptom of overfitting. In the context of universal induction, that's usually considered to be because the system is not complete. Why do you think that is the case? What is your interpretation?
Well, I mean, it's overfitting in a very broad sense, right? Because I believe these guys have done proper in-sample, out-of-sample testing. So I'm not sure it's, in a very broad statistical sense, it could be overfitting. I mean, in the sense that I don't know, what do you think about that, Josh? Would you call this overfitting?
It's hard to say. I don't have an opinion at this point.
Yeah. I mean, I did think your earlier comments were along those lines, though, in the sense that you can think of it in a way as overfitting to a certain type of data, even, because we, as human beings, as you said, we see noisy, messy images, we see occluded images, and we may get a lot of internal noise from this noise inside our brain of various sorts. So we get a lot of noise and mess already, and we adapt our processing algorithms to that. Whereas if you if you train an algorithm or design an algorithm based on clean data, then you're going to get the different results.
So there's three things at least at play. One is we have different training data.
Yeah.
Second, we can build different hierarchies. This is one of the big problems. And then the third thing is that in between the feature hierarchies, we have connections. It seems, for instance, that vision is basically inverse rendering, which means we have to come up mentally with some kind of scene graph, and on that scene graph, we have to propagate something like the coordinate frames between the features. So if I see the nose in your face will inherit its position or its pose from your face. And if you want to learn this with a convolutional neural network, it's tricky. Convolutional neural network, usually what it does is it has some pooling to this particle pose of your nose, so we can still recognize it if you move your face. But this is not the way to do it. It means that in most cases, we will still be able to recognize you. So the network will perform relatively well, but it's not the optimal way to treat the data.
Yeah, to answer your final question, I mean, I thought I tried to do that in the talk, which is that my intuition is that the reason you get these weird pathologies is that these networks in their current form, they're not really building up a feature hierarchy of the kind that is most naturally imminent in the data. I mean, supervised learning can lead to very many strange things, right? Like if you're trying to classify men versus women, based on a certain corpus, you could focus on their hairstyles or their dresses or something, and on certain corpora you get a very, very high accuracy. But then that's not what we think is the crux of the difference between men versus women, which has to do with the kind of data you're feeding. This is a much subtler phenomenon, but it could be conceptually along the same lines. But it's still being unraveled in the literature now. This kind of thing is getting so much attention by so many well-funded researchers. I guess in 5 years that will be understood a lot better.
Yeah, well, maybe sooner. Some comments, quick comments on the question. Well, it could be due to two things. First, as you mentioned, due to inadequate modeling of the topology of the visual system in the human brain. And second, inadequate modeling of the neural dynamics. I believe the latter might be more substantial. But of course, there is this fact that the visual system is composed of many modules. So the brain works with much richer set of features, like motion, texture, color, a lot of things, stereotypes, of course. So that's why the brain is much more resilient to such errors, because there are many more features. But also because of the neural dynamics, and even if you consider just the 2D image recognition task, even then I think the proper universal induction approximation should do much better. So that's something to figure out in the future.
Yeah, I have no doubt that a good universal induction approximation would do better. The reason that these deep networks have been popular in the last 5 years and not 20 years ago is basically that computing power is now there to run these things at scale on large corpora, right? And we don't yet have the computing power to run a good approximation to universal induction, do we? To find a cheap enough good approximation to universal induction is kind of a challenge.
Okay, anyone else? Okay, let's thank Ben again.